So, model making with digital fabrication. So digital fabrication is a design and manufacturing workflow where digital data directly drives manufacturing equipment to form various part geometries. The data most often comes from CAD, which is computer-aided design, which is then transferred to CAM, computer-aided manufacturing software. So essentially what this is saying is that anything that you design on a computer is CAD, and then you can translate that into become something physical via CAM. And essentially what we're going to do, we're going to go through these elements today. So we're going to look through the core architectural model types. We're then going to look at additive and subtractive manufacture. We'll look at some best practice and considerations for how you can engage with these and use these in your own models. We'll look at your internal and external facilities, what you can access. And then we'll show you how to prepare your files for the digital fabrication. And as I said before, I do have a few examples of some models that we can hopefully play around with today. So getting straight into it, architectural models. Essentially, we have three main types. So we have the concept design model, which is essentially where you're right at the beginning of a project and you're just doing initial form finding. So these are typically analog in nature. You wouldn't usually use digital fabrication for these because you wouldn't have any other data to drive these as an input. Unless you're doing something in, say, Grasshopper, or maybe you've obtained some data, like some site data, and you're doing some analysis, but that would still form part of a concept design model. The next type would be the working design model. And this is kind of an iterative model. So it's the next stage up from concept, but this one's actually informed by, say, technical drawings, other data sources, such as like who's using the site, what materials, etc. And this is something where you might build it just at first to explain the 3D volume of the space and how people circulate, or you might have another function. But essentially, it's one that you kind of tear down and you keep on adding to. So you'll kind of keep coming back to tweak it until you're happy with it. And then that would then lead on to a concept design model or concept presentation model. And essentially what this one is just where you finish the project and you're trying to communicate some kind of end scheme. Now, that then breaks down into purpose. So we know the three stages. We know that these ones are kind of relevant to the stage of the project. So beginning of the project, working on the project, communicating the project. But essentially, each model needs to have a purpose. So to begin with, we've got topographic modeling up in the top left. I'm sure you can understand what this is straight away. It's essentially built from a topographic map, and it's showing us the height data of the land of the site that we're working on. And typically, these will be quite large-scale models, or small-scale models with large numbers. So you might see these from 1 to 1,000 to 1 to 10,000 if it's a very large area. You might also see these in quite a small scale, but typically if it's a smaller scale model, you would then be looking at landscape design, in which case you start seeing more elements of detail. The topographic is just where you're kind of separating the layers out every meter or every 5 meters, depending on the data, and you're showing that terrain, changing terrain. You then have exterior design models. Again, quite straightforward what these are. These are purely just to communicate the exterior of your buildings. So these might communicate things like facade details. It might just communicate volume or form. But essentially, these would be usually between 1 to 50 to 1 to 200 for an entire building model. And typically, these would have a good level of detail to an extent. So you'd be able to see things like windows and doors at 1 to 50. You probably wouldn't see them at 1 to 200 unless you're 3D printing it in miniature. But it's just to kind of communicate that exterior space. The interior models, or commonly known as section models, again, these can come in various forms and different styles. But typically, these are to communicate the interior space of a scheme. And these ones can communicate things like fittings and furnishings, materials, or it could simply be just to communicate the interior space. So it depends on what it is that you're trying to communicate. But again, you'll see these ranging from 1 to 10 to 1 to 150. The most common, I would say, is actually 1 to 20 or 1 to 50 for those. We've also got landscape design. So again, landscape design is different to topographic maps. So these ones essentially would, I'm saying the word essentially way too many times. These ones would essentially give you quite a bit more detail. So for instance, I might be having a representation of materials on these. I might be having different planting specifications on them. I might be having some basic infrastructure. So things like road locations and maybe some block model housing. It's not quite a site model, it's a bit further zoomed out than that. But typically you have these at either end of the scale and not usually in the middle. So for instance, you'd have a small scale landscape, in which case it might be something like a garden or a small area that you're building up. And you might have some details at 1 to 100 there. Or you might have a really, really small scale model up to like 1 to 5,000, where it's communicating a much larger area. For instance, like the west coast of England or something. We then move on to site model. So site models are, again, really, really useful. For these, you would usually have block massings around your site. So they're sometimes called context models as well. So usually you'd have like a block extrusions to represent the surrounding buildings. And these are usually up to about 1 layer around. So if your building's in the middle, you'd have 1 row of buildings all the way around it. You wouldn't usually communicate much further than that, unless there are multiple sites that you're designing. And these again would be a very low level of detail, so 1 to 500 to 1 to 1000. And then again, these would not have much detail in terms of things like windows and doors and people and things, but it would have detail within your design, kind of centered in the center. Centered in the center? Your design in the middle. You see the very next one is urban design. And again, urban design is quite different to site model. So where site model is purely just to show things like location and to have a bit of contrast there between new and old, urban design will actually have a lot more detail in terms of its surroundings. So on this, you might have actual people, you might have things like cars and vehicles. The key thing with urban design is you're showing the interaction of the space. And again, because you're trying to show detail, these would then be a like 1 to 50 to 1 to 500 scale. 1 to 50 is what I would say is most common for urban design. So they're the kind of main ones, they're the main purposes that you kind of come across, which is kind of trying to convey things like location and such. But then we move on to the more interesting ones. So for instance, we have structural models. You can see there's this model of the Metropole parasol. These would again be kind of 1 to 20 to 1 to 100. And these would actually represent the way that the structure would work in real life. So in this one, this is an interlocking structure. And this one was laser cut. So that would have grooves in both directions on the top of one of them and on the bottom of the next. And they would essentially just slot together. We then have conceptual models. So these ones again are where you kind of form finding. And you're just exploring ideas and techniques at this stage. So it could be as simple as doing shadow and light studies across a piece of paper. Maybe you're cutting into it across specific patterns to generate volumes and kind of internal spaces. It's completely up to you, but it's more exploratory model making. And again, these would either be 1 to 10 to 1 to 200, depending on the nature of the thing you're trying to design. We then have abstract models, which I absolutely love. We got some fantastic ones on display here in the Humanities building at UOM. And that's what this picture is of here. So this one is a laser cut model from a book. And essentially, they've captured all of the offcuts of this, all of the kind of void elements, and stuck them together, which is this piece on the left. I'll find my mouse. It's this piece on the left just here. And then the piece on the right is that negative space. And I think this is an absolutely stunning model. And these would usually be tied to some kind of narrative. So you're not trying to show accuracy as such with these, but you are trying to communicate the kind of main point behind a scheme. So it's the equivalent of like a party sketch, for instance, but via models. And then the final one, of course, would be construction details. So showing how something is actually constructed in real life is going to be really, really useful. So different to a structural one, because a structural model is something that you could potentially test. You could actually put weights on it. Whereas a construction detail was mostly a visual representation of how something would be constructed. So for instance, you might have like insulation layers, you might have various cavities, you might have different floor finishing levels. You might be showing elements of structure coming up through the center of the floors and showing how they join to beams and struts. So again, it's up to you what it is that you're trying to communicate. But typically these would be 1 to 5 to 1 to 20 in scale. So essentially, what is the point? Why are we trying to make models? I'm sure some of you are probably going to say, because my tutor told me to, and that's fair enough. You know, we do ask you to make a lot of models, but essentially there's a very big reason why we make models. And what you need to ask yourself is, what are you trying to convey? You know, use this as a tool for communication. What is it that you're trying to get across? So are you trying to show a new concept in its surrounding context? In which case something like a site model or an urban model might be quite useful. Are you trying to show a relationship to the construction method? In which case maybe a structural model or construction detail model might be quite useful. Is your focus on the materials and processes being used? In which case maybe you're going to be doing either an exterior model, a structural model, a construction detail, or an interior model. So again, there's different things that can influence what it is that you're going to be making. If you're showing the circulation of a space, again, that could be any one of those. Or is it simply just for iterative form finding? In which case you wouldn't be using digital fabrication, you'd probably be doing this one analog. But essentially, it all comes down to the scale and level of detail. So once you've justified the message that your model needs to convey, you should be identifying an appropriate scale to make it to. So for instance, if I'm going to be having, if I'm trying to show people walking around my space and interacting with it, I wouldn't be going above 1 to 50, for instance, because you're not going to see people at 1 to 50. I know you can get 1 to 100 and 1 to 200 scale people, but usually at that scale, you're not going to see really what they're doing or how they're using that space. But essentially, the smaller the scale, which is the higher the number, like 1 to 200, 1 to 500, the less detail you're going to see. And again, same thing with the actual details within the model itself. So you wouldn't see a door or windows on like a 1 to 500 scale model, but you would on a 1 to 50. So again, think of what it is that you want to represent. And then lastly, also consider the fabrication processes you may use to convey this and their strengths and limitations. So some of you might be thinking of exploring some 3D printing. And again, we're going to touch on the strengths of these shortly. But if you're 3D printing, it's very important to know the limitations of the machine. So for instance, if I wanted to 3D print an entire site model, I might be limited by the build plate dimensions of the 3D printer. Or maybe I'm going to be trying to print something super, super small, and maybe the 3D printer is not quite small enough. But maybe the laser cutter could handle it. So again, think of what it is that you want to communicate. And then lastly, we have aesthetics. So regardless of the message and the scale, the aesthetic style is ultimately up to you. It's up to you to bring your own design language to this. I would say, though, try to show as much contrast where possible. So for instance, you might show a bit of a different color between new and old objects, or maybe it's the use of material or level of detail. Something just to highlight what the key message is within your scheme is always useful in a physical model. A good example of this would be basic block massing, like surrounding context, with a detailed concept model in the middle to show its location. Something like that, again, would easily convey a message. I would say, though, try not to overuse a single process or material. So the most common one for this is where people try to make a 3D digital model, and they say, right, I'm just going to 3D print the whole thing. And they'll send it off to the workshop, and it will get printed, and you'll probably get a low grade. Reason being is that it just looks lazy. So is it communicating anything? If you have an entire site printed in the same level of detail, same color, and it's all just a big block of plastic, that doesn't communicate anything to me. So again, don't be lazy, put that extra effort in, try and interrogate what it is that you want to communicate. So that brings us on to the actual equipment. So additive and subtractive manufacture. Now I'm just going to pause there for a minute, mostly because I'm losing my voice already. But I just want people to type into the chat what you think additive and subtractive manufacture are. Who here could explain it to me? Just going to open up the chat. Any guesses on additive and subtractive manufacture? Or I might have to start picking people at random. Yep, I'm going to do ip dip do. Right, I'm going to pick on Cameron. Do you want to unmute for a second, Cameron, or type in the chat? Let us know what you think they might be.
Hello. Yes, I was just actually typing then.
Oh, sorry.
I was going to say additive manufacturing is the process of adding material to an empty plane through an almost one-to-one pairing of material to product. And subtractive is removing from a block of mass, causing a lot of waste.
Yep, I would go with something like that. I think that's a pretty damn good explanation. Oh, just muted myself. Don't do that. Yeah, so if we have a look, essentially we've got laser cutting. I'm going to go through each one in order. So essentially we've got laser cutting, which is a form of subtractive manufacturing. So the reason this is subtractive is because essentially you have a block of material. So it might be plastics, it might be wood, it might be something else, it might be metals. And essentially you're going to be subtracting or cutting away from that block or that volume to end up with an end result. Something like these on the screen. And essentially the way this works is it's just using a beam of light or essentially a laser to subtract or cut along a vector path. And even though we call it laser cutting, they don't only cut. You can actually do a hell of a lot with laser cutting. So for instance, if you were to set up your lines correctly, anything that you color red in your files is going to be a vector line cut. So it's going to cut those shapes out. Anything that you color RGB blue is going to engrave. So it'll do it to like half the depth, or you can lower the power of the machine to do it even lower. And anything that's colored black, you can actually do as a grayscale or raster engrave or etch. So I'm going to show you some examples of that in a second. Essentially, the key things you need to be aware of here are removing things like double lines and duplicated geometry. So if you've produced a technical drawing in something like AutoCAD, Vectorworks, Rhino, etc., Revit, make sure you don't have any duplicate lines in the same locations. Reason being is just that if you're trying to engrave something, if the laser has to go over that line multiple times, it's going to do that darker and deeper than the rest. And you're going to end up with quite a nasty looking model. I would also say try and join the lines up where possible, because that way the laser cutter head itself will follow those paths and you'll get more consistent cutting and engraving. I'd also recommend to work with lines, polylines and arcs in your software. Try and avoid splines where possible. And in fact, that one's a good rule of thumb. Regardless of what method of digital fabrication you're using, splines are generally a big no-no. So most CNC machines don't like them, laser cutters don't like them, water jet cutters don't really like them. There are a few exceptions to the rule, but it's very, very rare. And then final things would be, just before you export, I would say make sure your line weights are set to 0.05, because that's what they need to be for cutting and line etching. And then exporting it as a 2007 DXF. And I'm sure some of you are going to argue with me about the DXF type on this. And I'm sure if Scott's watching this back, he's going to say, no, not 2007. Yes, 2007 is the absolute best. Reason being is they changed the way that they encode these files since 2007. And a lot of older machines now no longer work with this. So for CNC work, you'll find R12 works the best. For laser cutting, 2007 is easily the most consistent. So if you're going external, that will always work. So just having a look at the things that this can output. We've got some examples here over on the left. So for instance, cutting, as I said before, setting your lines to RGB red will actually cut the objects out. Line weight should be 0.05. And if you're cutting out multiple components next to each other from a single sheet, just try and allow a little bit of space, like at least 2 millimeters between them, and then you should be good to go for those. Again, if you wanted to do any kind of engraving or etching, you can do that by setting your vector lines as blue, so RGB blue. Line weights again should be 0.05, and again remove double lines for consistent engraving, but also to reduce time. And then the most interesting one, which a lot of people don't realize you can do with laser cutters, is to actually do 3D etching. So if you've got a grayscale image, or if you just had like a solid black infill or something like that, essentially you can etch this to different depths. So anything that's colored white within your image isn't going to engrave at all, or it's going to etch very, very lightly. Anything that's set to 100% black is going to etch and engrave the deepest. Any level of grayscale will etch to different depths between the black and white. So you can really use this in a clever way. It's essentially like using a height map, for those of you that are familiar with height maps. But again, something to consider. Another thing worth mentioning as well is if you're engraving a lot of vectors, so let's say this one in the middle where you've colored everything blue, let's say we've got 3,000 lines that we want to etch, it might actually be faster just to set those to black and let it do a raster etch instead. Which means that the laser cutter head's going to go whizzing from left to right, top to bottom, just like a standard printer would, rather than trying to follow all of these lines around, which saves a lot of travel time on the laser cutter. In terms of preparing files for this, firstly, I would say have a look at the materials that you're going to be using. So for instance, you should never use corrugated cardboard because the little corrugated layers in the middle, they kind of have pockets of air, and when the laser cutter head hits those, it kind of just starts fires happening inside the machines. And we're not a fan of fire when we can help it. So we're not going to be laser cutting any corrugated cardboard. Regular card is absolutely fine though. But again, talk to the technicians to double check because some of them do come with coatings. So again, it's good to check this stuff. You can etch some metals, but you need to be really careful what it is. You can't cut the metals on our machines, but you can etch them. But just make sure you're not trying to etch anything like magnesium. I'm sure everyone remembers back to GCSE science. What happens when you light magnesium? Flares up like the sun. We don't want that to happen in the laser cutters. And again, try and avoid things like foam core, again, just mostly because they're super flammable. But pretty much anything else, so things like sheet woods, like plywood and MDF you can use. You can use things like acrylics, they're super useful on those machines. You can also do things like card, you can do various types of foam, although I wouldn't actually do foam. Foam's nice to etch with a laser, it's rubbish to cut because it's too hot, it just melts it. If you're doing a really low powered etch, it's really, really effective. But again, talk to technicians, they'll be able to guide you through this, you'll be absolutely fine with it. But again, in terms of file prep, if you're exporting this from AutoCAD or Rhino, which are the two software I would use for fabrication, you should always explode your blocks because otherwise they'll come into the laser cutter software all black. You won't be able to read the color of the vectors or the line weights. So explode all of your blocks. Ungroup and unfreeze any layers because they won't be read by the laser cutter. If you're using AutoCAD, you can type in the command overkill, and this will remove duplicate lines. Or you can do the same thing in Rhino by typing in cell dupe or select duplicates. This removes duplicate objects. Again, in AutoCAD, if you're using constrained, if you're using parametric constraints in your models, select your entire model and type in del constraint, which deletes all the constraints. And again, these should now be able to be read by the laser cutter. I would recommend your geometry is separated onto 2 or 3 layers, depending on what it is that you're etching and cutting. So if you're doing just a standard cut and engrave, you would have 2 layers, red and blue. If you're doing a cut, engrave, and etch, where you're having a raster image, I would recommend you have 3 layers to separate those out. Line weights again, all 0.5. Check the material stock before laying out your drawings. So again, talk to the workshop staff for the place you're going to be getting it fabricated. They'll let you know what materials are going to be in stock and their dimensions. You would then draw a rectangle to represent that sheet in AutoCAD or Rhino, and then you'd lay out your components in the most efficient way to remove as much waste as possible, reduce waste even. Final things, of course, would be to ensure your drawing is the correct scale and fits within a laser cut bed. So it's very common to draw your objects at 1:1 scale if you get to scale them down. And of course, trying to fabricate that 1:1 is going to be very, very expensive. You need a very big machine. And of course, lastly, save as a 2007 DXF. Oh, I'm going to catch my breath for a second. There we go, close enough. Right, next one would be the Flatbed CNC. So Flatbed CNC, it's really similar in some ways to the laser cutter. It's another form of subtractive manufacturing, but instead of using a beam of light, it's going to use what we call a mill bit. And a mill bit looks just like a drill bit, for those of you that have ever used a drill. But instead of kind of cutting downwards, it cuts sideways. So cut downwards just a little bit to plunge into the material, but all of its cutting power is translated into the X and Y kind of dimensions. And essentially, there's a few things you need to be aware of with this. So it's really similar to laser in terms of setup. So removing any double lines and duplicated geometry, join lines where possible. But there are a few more things you need to be aware of. So for instance, if you're cutting out a particular shape like these ones, you'd want to make sure each individual shape is completely joined up and closed. So the reason being is that because it's not going to be cutting it with a really, really super thin beam of light, it's going to be cutting it with a mill bit which has a thickness or radius. Essentially, you need to decide whether you're cutting on the line, inside the line, or outside the line. And again, I'm going to show you a couple of problems relating to this in a sec. As before, work with lines, polylines, and arcs. Always avoid splines, especially with CNC. Lines should be 0.05 line weight. I don't think it actually does matter too much for the CNC, but most places will say either 0.05 or 0.01. And again, 2007 DXF is fine. You might want to export it as an R12 DXF if you're sending it out to an external company, just because they might be using older equipment. But again, something to consider. Now, some of the problems you're going to run into with this would be things like internal corners. So this is the most common issue. Let's say we're trying to fabricate that interlocking structure from that image at the beginning. If I wanted these objects to slot together nicely, I need to have nice flat edges. So if we look at this middle image, we can see what we're trying to create in this top left part here. So we want this object to slot down into this groove. We want it to sit all the way down so it sits flush at the bottom, yeah? At the moment, because the mill bit is rounded, because it's cylindrical in nature, it's not going to be able to cut exactly the shape that we requested in the software. It's going to be limited by the radius of the mill bit we're cutting with. So there's a couple of ways around this. The easiest and most accurate way, I would say, is just to chisel these out. So send it for fabrication. It's going to do 99% of the work on the CNC. Then I would just go around and post-process it with a chisel to flatten out these edges, get them nice and sharp. If you're not worried about it looking super pretty, then you can add in these little plunge cuts. So these would usually be drawn as like a circle in the file, and the machine would essentially plunge down into these. It would just plunge the mill bit straight down and cut these out, almost like you're drilling a hole into something. And you can see a few examples of how these might look. So top left one here is what we want it to look like in the end. Top right is what we call the Mickey Mouse ears. This is quite common. You'll see this quite often, just because it's easy to place the center of a circle onto the corner. It's actually not the nicest way, and it's not the most structural way either. Another one would be this bottom left one. I don't believe this has a name, but again, we wouldn't want to fabricate it in this way, because as this interlocking piece comes down, it's going to be resting on a really tiny little narrow nose. And it's going to crush that. You know, it's going to reduce the tolerance of our file. But the nicest way, I think, is to do it in the dog bone way. So what this one is it's placing the circles in, so it's doing plunge cuts as we defined before. But the center of it is actually slightly higher than the corner, and it's rounded out in such a way so as the object can sit flat, but it's still got the maximum surface area, and it's cut in the opposite direction to the interlocking element entering it. So hopefully that makes sense what we're trying to achieve with that. So again, in terms of limitations, you're limited by that mill bit diameter. I'd also recommend that you place components at least 12 millimeters apart on the sheets. So as you can see, this sheet over here, we've got quite a bit of distance between. Again, the reason for this is because if we're cutting outside each of these shapes, we don't want things to suddenly start floating around if they overlap. So again, something to be aware of. Or you don't want them to be butted up against each other and to accidentally cut into each of your components because they're too close together. And again, make sure everything is inner and outer closed curves. So for instance, if I'm cutting out these shapes, the outer boundary, I would set that to be an outer cut. Everything on the inside, I'd probably tell to be an inner cut. So you need to be really careful with your layer management with this. We'll talk about those in a sec. I don't think there's a huge amount more to say about CNC other than what materials you can use. So again, sheet materials like woods and plastics are really common. You might also want to use various types of foam, although for 2D CNC, that's not really very common, unless you're doing something like making some temporary molds to work with concretes and things. I'm sure everyone's seen those on Instagram, where they're carving out the shapes out of foam, then they're pouring concrete, melting away or pulling out the foam, and then you see this nice, beautiful concrete relief. Absolutely stunning stuff. Highly recommend you go search for it. You'll lose a couple of hours of your life, but it's totally worth it. But yeah, essentially, when it comes to the materials, just always talk to the technicians. They'll always know what's best for those machines. Again, laser cutting is really good for small scale stuff, whereas CNC is more kind of medium to full scale stuff. So CNC is what you'd actually probably use for fabrication in practice. You can make one-to-one scale objects with this. So again, it's a really nice one to use. You can also etch with CNC as well. So you could set up different layers to do different things. So for instance, you could have color-coded layers. One it represents an inner cut, another one it represents an outer cut, one it represents the plunge cut, like for these internal corners. And then you might have different engraved layers. So you might have one bit engraving to 2 millimeters, one bit engraving to 5 millimeters, so on and so forth. So key thing is just be super clean with your layer management. Same file prep as before. Explode all your blocks, ungroup and unfreeze your layers. If using AutoCAD, use the overkill to remove duplicates, or use delete constraints to delete your constraints. Make sure your drawing's the correct scale. Check the material stock before you send it for fabrication. And of course, make sure you're talking to the technicians. Now, the other side of CNC is where it starts getting a lot more interesting very, very quick. And this is where we have things like 3-axis and 5-axis CNCs. So 3-axis are the most common. It's very similar to the 2D one, which just got a little bit more control over its plunge cut on the Z-axis. And these ones wouldn't be using things like DXFs. These would be using 3D file types. So these would be things like your STLs, OBJ files, and 3ds files. But again, it's another form of subtractive manufacture. There's various materials you can use with this, but there's also quite a few limitations as well. So I'm going to show you, in fact, if I just jump straight to the next page. Annoyingly, it's quite small. Can you zoom in on PowerPoint? Yeah, you can. If I zoom over here, there we go. If you look at this section over here on the left, you see most of the common issues that you're going to come across. So we already know about this issue here, about things like inner corners due to the diameter of the mill bit. That's going to be a common issue, including going between 3D objects as well. So it's going to kind of round these out instead, so something to be aware of. You're also then limited by the height of the mill bit. So essentially, the wider the mill bit, the higher it can be. If you're doing really thin detail work, the thinner that mill bit needs to be, which means the lower that mill bit needs to be as well, because otherwise it will snap as it's cutting the material. So the smaller the mill bit, the lower the material height you can use in the machine. So you need to kind of factor this in, I think, when you're trying to fabricate. So typically the way these would work anyway would be that you would have what we call a rough pass and a smoothing pass. So you would give the technicians your 3D file. They would then generate a rough pass across it first to remove the bulk of material, which would then hopefully go on to be recycled. And then they would swap out the mill bit for something thinner and a bit more detailed, and it would generate what's called a smoothing or finishing pass across the model. And that gets you these really nice smooth 3D reliefs like this one here, this white one. But there are some issues that you're going to run across even then. So for instance, things like undercuts are really common. Let's say, for instance, we've laid this object down. I can see that it's got a bit of a shelf to it, or what we call an undercut. Where this CNC machine can only plunge on the X, Y, and Z axis, it can't get underneath that area. So instead, where it's got this cut coming down here, we'd actually just do that just straight down. It can't cut underneath. If you had a 5-axis CNC, then it might be a different story, because a 5-axis would allow you to rotate the model as well. So not only rotate the tool bit, or the mill bit, but also the model, and you can start getting into these little areas. But again, try and avoid undercuts where you can. There are ways around it, however. So for instance, if you divide a model in half, maybe you're going to mill the top half, like this one on the blue one there, mill the same shape again, and then you could join them together. That could be a solution. Or alternatively, you could do a double-sided mill. So if you made like a frame around this object and had like a little strut to connect this object to the frame, it could cut it out, and then you could flip that over, and then you could mill the other side, as long as you can align it correctly. We don't recommend doing that where possible. Try not to do double-sided mills. They're really, really painful to set up, but you can get some great results. But again, kind of common things in terms of materials for 3-axis CNC. You're going to be looking again at woods and plastics, are quite common. Foam and clay, also very common for these. Sure, some of you might have seen these concept models for when they're designing cars, for instance, when they're making the aerodynamic models. You know that red clay that they tend to use? That stuff is fantastic on CNC machines, and that's how those models are made. And again, you can also cut some materials, some metals as well. So some low-grade aluminiums you can cut, but typically you wouldn't want to go above that unless you've got a dedicated machine for cutting metals, because typically they need to be cooled with water and you have special cutting compounds, etc. One thing that is useful for CNC work, though, is that you can also make molds from it. So let's say, for instance, you are doing something quite iterative, or maybe you've defined a form and you just want to be able to cast this in a mixture of different materials. Don't know what happened there. Maybe you just want to cast the same object in different materials to test their properties, for instance. In which case, making a nice solid mold, something like this, you could carve it out. You can make little locating pins or locating holes so everything aligns nicely. You'd allow a little hole to pour a material into it, and then you've got a reusable mold, which is fantastic. So you CNC it out of something tough like Necuron or some form of metal like aluminium, and then it's just a case of pouring in things like your concretes, your plastics, so things like injection molding you could do with it. There's so many applications that you can do by combining these machines together. I have listed a few things here for file prep that might be quite useful, and these are going to be the same things for 3D printing as well. So what I'll do, I don't know if you can see this floating on my screen. I'm just going to move that out of the way just in case. It's just my little Teams window. Nope, you can't. Perfect. But essentially, these are my top commands in Rhino. We're going to be using these a little bit at the end. Top commands in Rhino for fixing 3D files for fabrication. So for instance, I would always convert your geometry to a mesh first, rather than having it kept as solids, just because when you export complex models, they become huge in file size. So if you convert it to mesh first in Rhino, you can then control the polygon count, keep the file sizes down. It means the machine's going to process it easier, and you have a much higher chance of success of your model being fabricated. Again, reducing file size, there's a separate tool for reducing polygon counts. If you're 3D printing or CNC machining, typically you'll always want to work with watertight models. So again, you'll be able to tell it to fill all the holes in the model to close it. And then you can do things like fixing normals where surfaces are facing the wrong way. You can identify any issues like self-intersections and overlaps. So again, I would have a look at these tools down here. The commands for them are listed in blue. Make a note of the little underscores before some of these. But most of these are going to be under the mesh drop-down within Rhino. And again, when exporting, you do these as an STL, OBJ, or 3DS. And when prompted, choose binary. Right, let's go to the next one. So next one at last is 3D printing. So 3D printing is not a form of subtractive manufacture, it is a form of additive manufacturing. So as was explained earlier, 3D printing will create a physical model one layer at a time by extruding filament or curing resins or fusing powders to create a solid object. So you can see this one processing here on the left. This one is just extruding this resin that we saw at the beginning, this filament, sorry. It's melting it out of essentially what is a hot glue gun, and it's drawing this one layer at a time. And that bed's stepping down each layer. The extruder then moves and prints the next layer, and you end up with a nice solid object at the end. Now, some objects will require things like a scaffold, because you can't 3D print in thin air. Again, we'll talk about that in a minute. But it might determine the way that you go about making your 3D printed models. A few things in terms of best practice. Again, try avoiding overhangs. Oh, wrong button. Try avoiding overhangs where possible. So we did speak about overhangs with the CNC just now, the little bit where the thing can't get underneath. On this one, it's not that the print head can't get underneath it, but rather that there's nothing to support it. So for instance, if you're trying to create like a cantilevered structure, you would need a scaffold underneath while you're securing it in place. So quite straightforward, I think. There are, of course, ways to add scaffolds in the softwares themselves. So don't worry about that too much. You can tell the software to generate a scaffold, and then you can just snap it off the model after. You might also be limited by the printer's build volume. So again, depending on the process you choose, you might run into problems with it not being able to print the whole model, in which case you need to split it up into smaller components, or maybe you just need to reduce the scale. So it's something to consider. Try and reduce the file size again, make sure it's watertight, make sure the normals are aligned. You can also follow all of the CNC processes back here. So all the file prep, it's the exact same for 3D print, there's no difference there. And again, save as either STL or OBJ for 3D printing, like standard 3D printing. Or if you're 3D printing in color on like a powder or polyjet printer, let's say you've baked in textures into your 3D file, you can 3D print those in color by exporting as a WRL, and it will bake those textures into the geometry. Now, I've actually been handed a few slides, which is really, really nice of Print City. So they're putting together a nice new guide for you all. It's one big super master guide on 3D printing, and they've been massively upgrading their facilities. I'm going to talk to you about them as a resource shortly. But essentially, they've outlined a few of the most common problems that you come across. So the first type of 3D printer and the most common type is FDM, which is fused deposition modeling. And this is the one that I explained is a bit like a hot glue gun. So essentially you have this material running in through the top, which runs into like an extruder or a hot nozzle. This then gets squeezed out and it will follow the shape of a layer. So if you've got a 3D model, it will slice it up into layers and it will see that each layer is an image. And then it's going to literally try drawing that per layer by extruding plastic. Then the bed steps down one layer at a time, it draws the next layer, so on and so forth. You've got yourself a finished object. Now over here on the right, you see some of the issues with that. So for instance, this print over here on the right starts off really well. It's printing one layer at a time, going inwards towards each other. You start to see a few little scaffolds on the underside where it's trying to support itself, because once it reaches a certain height, or once it goes above 45 degrees, it's going to start collapsing. And then, of course, the higher up you get, the more extreme that becomes. So you see this X over here on the right. If we 3D printed this without these supports, these scaffolds, then realistically, as this gets higher and higher, this X is going to start drooping more and more because it can't 3D print in thin air. So something to consider. Again, it's going to be printing in layers. So the actual surface finish of this is going to be kind of bumpy, like this outer edge here. This is a good thing and a bad thing. I would say it's mostly a bad thing, if I'm honest, because it means it's going to be a lot of post-processing required if you wanted to fix these things. So you could use a lot of spray fillers, are quite commonly used. You can spray these in to fill in these little gaps, then you can sand them smooth to post-process, and then you can paint them, do whatever you want with them. Or you just want to sand it flat to begin with. Again, something to consider. And another thing to consider as well is try not to use the maximum amount of a build plate. So for instance, this model here, this might be fitting within the build dimensions, but because it's one flat surface area spread across the whole thing, essentially you might start getting warping edges. When the material is hot to begin with, as it cools down, it can't keep up with the heat of the plastic above it. So it's going to start warping edges and you end up with a lot of failed prints. So again, there are ways around this. Changing the material, for instance, is a common one. If you change it to ABS, or if you use various additives on the printer, that can help resolve these issues. Splitting the model up and printing it as a smaller volume at a time, again, will help it. Making sure the build plate is a heated build plate, again, keeps these temperatures nice and warm, which keeps it flat. So again, things to consider. Now at Print City, we're going to be talking about Print City again in a bit, but Print City have an entire army of machines. They've massively upgraded their facilities. And their most common machines, I would say at the moment, are probably the Ultimakers, which are the FDM type, and you can see the build volumes for these here. And again, the layers in between, these ones back here in the bottom right, the thickness of these layers just depend on the resolution you print to. So the most common ones for FDM are between 0.1 millimeter layer thickness up to 0.3. These are the most common. And that's what can be done on these. So available materials, you can print in PLA, which is polylactic acid. You can print in wood filaments, which are mixed with PLA. You can print in TPU, which is kind of flexible. You've got ABS, which is more kind of industrial. It's what most injection molded plastics are made from. You got PET or PETG, which are kind of food safe plastics, which are really nice. Then you got like things like PC and nylon. I'm not going to touch on all of these. I am going to make this available, this document, so you can have a proper read through yourself. But again, PLA is the easiest to print with because it has the least failures. It can be printed at a lower temperature as well. It's just a very, very nice one to print with. If you were to 3D print in something like ABS, however, then you could even use things like acetone to smooth it. So essentially what you do, it's very toxic, so be very careful if you do it. But if you 3D print in ABS, you can basically put it in the same room as acetone, put like a cover over the pair of them, and just the fumes from the acetone is going to be enough to slightly melt the outer layer of the ABS. And you get objects that look almost injection molded. Pretty fantastic stuff. Again, PET, very high impact resistant stuff, scratches easily, it's quite expensive, but it is food safe. So again, something to consider. Nylon, again, typically if you're printing in nylon, you wouldn't be using an FDM machine, you'd be using an SLS machine, which we'll talk about in a sec, just because nylon is a fantastic material to print with. TPU is almost like rubber, so it's a very flexible material, great for creating things like hinges and stuff like that, or flexible objects, things like O-rings and gaskets. Great stuff for that. Polycarbonate, again, similar to the other plastics. Good mechanical properties though. And then we move on to the next one. And to be honest, this is my favorite one. I've actually got a few of these 3D printers at home, the SLA ones. You can now pick these up online for super cheap. I think I paid about 200 for mine, or just under 200. And these ones print in resins. So rather than extruding plastic, what this does is it still slices your 3D file, but what it will do, it's got a little screen underneath, and it's going to shine a light in the shape of your layer. That light then cures a layer of resin, and then the build plate kind of steps upwards a bit, brings it out. It shines the next layer from your 3D model, and that cures to the first one. Build steps up again, cures the next layer, and so on and so forth. And again, you can see this process happening in the top right. So instead of printing this from the bottom upwards, it prints it kind of from the top down. Or it might just be a case of doing it upside down. So depending on how you want to print this, if you've got something with big flat edges, typically you actually wouldn't print it flat to the build plate. You'd actually want to print it at a bit of an angle. And there's a bit of a science behind it. I'm not going to go into that today. But if you did want to learn more information on it, strongly recommend you reach out to Print City. I've got their contact details in this guide, so you'll see them shortly. But they'll be able to help you with this. But benefits of SLA, the level of detail is insane. So typically you won't see any of those steppy layers, which means you don't need to do much post-processing. The level of detail, again, you can go super tiny with it. So you can print, I think it's down to 3 microns last time I checked, depending on the printer, of course. But in terms of limitations, you're kind of limited in terms of what materials you can use. So they always have to be resin based. So these are going to be your various kind of different plastics. Again, build volumes are also a limitation. So amazingly, Print City do actually have a huge printer to use. They got the Formlabs Form 3L, which can print 200 by 335 by 300. That is absolutely huge for SLA, good size. And again, anything bigger than that, typically you wouldn't be printing it on these machines anyway, but you could just split them up and or scale them down. But the things that you want to do for this is things like your little scale people, scale trees, detail elements, stuff like that is fantastic on these machines. Saves you running to the 4D model shop every 5 seconds. It's also worth mentioning that at Print City, I believe if components are under £3 per print, they're free. I don't think they charge you for them. So you actually get completely free 3D printing if you're clever enough with your materials and your objects. Again, there's some information here about the resins. I'm not going to touch on those too much, just because I'm trying to save a little bit of time, because obviously we didn't start only this morning. Good point, actually. So one thing with this as well, with SLA, the components will look really highly detailed, but we would recommend against printing less than 1mm in terms of thickness, at least for the main wall details. So anything structural needs to be at least 1mm thick. You can still do tiny surface details, like down to 3 microns attached to it, if you're going to see it. But don't just try printing something that's, say, 0.5 millimeter. So in terms of making a model, you'd scale your 3D model down first. You would then check your entire model to make sure everything's at least 1 millimeter thick. You would then think, do I need to divide it up further? For instance, if I was 3D printing the room that I'm in now, typically I'd probably want to take the ceiling off. Otherwise, it's going to fill the entire room with scaffold. So it's going to be much easier to print the roof separate and just stick it on after. So again, things to consider. So there's a few things happening in terms of 3D printing. A few things happening in terms of 3D printing in practice. I think it's really nice that Print City have put this together. So obviously 3D printed housing, it's not just on the small scale now. You can fabricate at full scale. And this home here became the first lived-in 3D printed home in the whole of Europe, which is absolutely fantastic. I've seen some very good ones of these. I've also seen some very bad ones. I've seen 3D printed bridges. I've seen all sorts. So again, it's about utilizing the equipment for what it's used for and utilizing it to their strengths. So some nice stuff there. And to be honest, that looks pretty stylish. I would happily live in that one on the right. I'd have no problems with that at all. But the great thing with this is it's very, very fast to fabricate. So compared to typical bricklaying, you could automate this to run overnight, for instance. You just mix up your concrete, pour it into the machine. You have someone that continuously pours, but the machine does all the rest. And you end up with super highly accurate components. This one's an interesting one. So this one's the Tokyo 2020 medal podiums. Essentially, pretty much the whole of Japan came together, recycled a load of plastics, and then they converted that into 3D print filaments, and they created all 98 podiums by 3D printing. So again, it's a bit of adapt and reuse. And if you want to see the process, there is a video down here. And again, I'll share this resource with you. It's not even just for architecture either. 3D printing can be used in other ways. So for instance, Adidas have used this quite a lot, or they're using it at the moment at least, to create the uppers of shoes and trainers. And again, it allows you to create these really, really complex geometries. And it will allow you to do stuff that you can't do with traditional fabrics. And of course, as architects, we still engage with things like membrane structures and tensile structures. So again, these can still be extremely useful for us. There's some interesting applications in fashion, again, mostly in terms of printing complex geometries and patterns. But again, there's no reason why these can't be applied to us. It's what we're using them for. But I'd be looking at people like Iris van Herpen, people like that are doing some really interesting cutting edge stuff with 3D printing. This one I really like as well. It's a coral reef restoration. So I'm sure everyone knows that the coral reefs are getting massively destroyed, which is disgusting, in my opinion, that people are allowing this to happen. But being able to 3D scan and capture these means that we can then 3D print them and preserve them. So it can help to preserve the ecosystems. And again, it allows us to create these porous, interesting rocky surfaces. Now, speaking of 3D scanning, Print City do have access to an absolutely fantastic 3D scanner. So for instance, you could 3D scan yourself, print yourself off in miniature and put yourself in your architectural models. That's always fun to do. But you can also use it to reverse engineer things. So for instance, let's say you've got a model of a car that you bought from 4D Model Shop, but maybe it's not the correct scale. 3D scan it, scale it down, print it back off on a printer. You've then got yourself the same model that you've paid for, but in a different scale. So again, this stuff can be extremely, extremely useful. Now, one thing I would get you to think about at this stage is in terms of the equipment on offer. I mentioned to you earlier, try not to 3D print everything in just one block color. Instead, try to combine some processes. So for instance, if we look at this one might be it might have started off as a contour model, like a topographic model at the bottom. Then they might have poured in some resin to simulate water. So this one would have just been cast. And then maybe there's some 3D printed structures on the top. So again, very, very effective, good element of contrast. I can see the land, I can see the water, I can see the structure or the scheme. This tells me a lot of information. And even having the people in a contrasting red, I think is a really, really nice touch. Again, this one's an interesting one. So this one is using a mixture of processes. So this one was using reclaimed timber as the base. It wasn't milled or anything. The center of it was, because they had to put some stuff in the center. But it's laser cut acrylic for things like the walls, little bits of CNC wood in the middle. And then for this wave is cast in resin. And this wave, I know for a fact because I worked on this. This one was 3D modeled in Rhino. And then it was subtracted from a block in Rhino. That block was then 3D printed and it was lined with resin-proof tape. And then it just had resin poured into it. And then it was just a case of putting that resin block on top of this resin there, essentially welding them together with more resin to get them to blend. And then you got this nice kind of resin wave happening. And again, that's all made possible just by 3D printing a mold, pouring resin into it, and then breaking away the remainder of the mold. This one, again, super interesting. So this one's using these 3D printed nodes. This one's more for kind of surface details. Then you've got laser cut plastics at the bottom because it needed to have accurate locations for each of these metal wire bends to come through. And this is actually a structural model. It's a really interesting one. We're not always doing it for small scale models either. So we could do this for full scale fabrication. So good thing with all of these files is if you can fabricate it on a small scale, 99.9% of the time you can fabricate the exact same file on a larger scale. So like with very minimal effort. So if I were able to CNC machine these ones were CNC machined. These were milled as kind of smaller components and chunks. Essentially, it's the same case of doing this on a bigger machine. And it's just a case of moving these into place, and then you probably bolt them together from behind or something. But it allows you to create these interesting complex geometries that perfectly match. So it gives you that extra accuracy. This one's, I think, is an interesting model. So this one, it's a laser cut exterior, and then they've actually just combined that with analog processes on the interior. So all of this was fabricated just by using a scalpel on the inside to carve out some foam. And then the outside was actually laser cut because they wanted a nice, clean, pristine box. And I know for the final one of this, they did laser etch details about the model, like who made it, what scale, where it's located, etc. So this is a really nice presentation model. And again, the contrasting color between the interior and exterior, it allows you to see what we're focusing on within the scheme. We know nothing exterior has changed. We know the focus is what's happening inside. This one I absolutely love. Super clean, minimalist model. But essentially what they did was they CNC machined a mold. They then poured concrete into the mold to create this element there. They then made a timber box around it, poured in resin to fill up all of this, and pulled away the wooden box. That leaves you with all of this element. Then these parts were a mixture of actually laser cut and a little 3D printed person sitting on the end. So again, super clean, but that is absolutely stunning. And of course, we've got more functional models as well. So this one is pretty much just using laser cutting, to be honest. But again, it allows you to have that precision within the models. Imagine trying to fabricate something like this by hand. It'd be an absolute nightmare. Obviously, yeah, you could do it. But if you're automating this stuff in software, and there are ways to make interlocking structures super easy, especially if you're familiar with Grasshopper. Again, you don't have to use Grasshopper, but if you are, you can do this stuff in minutes. It's super fast. You can lay this stuff out onto sheets to fabricate. But hopefully it gives you an idea of how you can start combining each of these processes together to create some outputs. So even this one, having a laser cut kind of building shell with laser etched windows, it still allows you to see what the building's like from outside to an extent, and where things like windows and doors are located. But no matter where you're looking at it, you'll always be able to see the interior volumes and what makes up this interior space. Now, again, I am going to try and power through these. I'm going to try not to keep you all too long. We're going to look at the internal facilities. So at MSA, there are 3 core places you can go to get models fabricated internally. So these are the B15 model making workshop, which is where I am today, in the Humanities building over at UOM. You've also got Print City, which is based over in the Turing building, I believe, which is just slightly to the west of where the Humanities and Chatham buildings are. And then you've got the Make More labs, which are located in the Chatham building. So these ones are on the first floor of Chatham. And essentially, we highly recommend you engage with all 3 of these, or at least pop in and visit them. All the staff in all 3 places are absolutely fantastic. Everyone is happy to help. This is their absolute passion. They're really interested to hear what it is that you're looking to make, and they want to help you to achieve it. So the B15 Model Making Workshop, again, is located in the University of Manchester Humanities building. There's a link to their website here. And again, there's some fantastic resources, again, about things like file prep, how to access workshops. You can also contact them directly via their website. I've actually put a shortcut to the booking form here, so you can book in a slot to talk to them about what you want to make. But the kind of stuff they have traditional woodworking tools, so things like your pillar drills, bandsaws, disc sanders, etc. I just realised I forgot to plug my laptop in and my battery's about to die. Give me one moment. I'm going to quickly plug this in. Hopefully it doesn't die in the meantime. If it does, I'll come back and meet you all. Find a plug socket. There we go. I think I made it in time. Phew. Hey, when that happens. Need to get a new battery for this laptop. Yeah, so the kind of stuff they do is all the traditional stuff. So things like, firstly, working with hand tools. So things like lathes and chisels and etc. They're not a huge fan of casting on campus, just because, especially for things like large casts and molds, it takes up a lot of space and it's very messy. So something like that you might want to do over in the MMU labs, just because they've got a bit more space for it. Or you might just wish to do it from home, but they'll at least be able to help you make the molds here. And they also offer things like vacuum forming, making those molds themselves. They do have 3D printers, they have CNCs, they have lasers. So again, there's a lot of stuff here that you can access. And it's a really, really nice space to work in. They also have a photography studio just in that door at the background there, if you can see that image. I highly recommend that whenever you make a model, as soon as you finish making it, go and photograph it, because it is 9 times out of 10 sod's law that someone's either going to knock into it or something falls apart, or maybe a bit of glue runs down or something. Photograph it at the earliest opportunity. Moving on to MMU Print City. So Print City works a lot with practice, but they are primarily formed by MMU, so Manchester Metropolitan University. And again, they're located in Turing House, and they've got their own website there as well. And in terms of the kind of stuff that you can access, they're 3D print specialists. You can access FDM, SLA, DLP, SLS, PolyJet, 3D scanning, etc. They have tons of facilities there. Just realized I didn't actually add a slide for SLS 3D printing. I don't know how I missed that. Essentially, SLS is similar to SLA in that it has it's not quite a bed of resin, but this time it's a bed of powder, typically a nylon-based powder. And instead of shining a light to cure it, it's actually using a laser to kind of fuse the particles together. That's the way SLS works. So bed of powder, it will laser etch one layer, bed steps down, puts more powder across, laser etches the next layer onto the first, and so on and so forth. And the benefits of SLS is that it doesn't require any scaffolds because it's sitting within a bed of powder. So I just wanted to quickly mention that one. But again, if you want to see what Print City is all about, pop in and see them, or just click on their website and check them out. They've got tons of information about their equipment, or you could feel free to just drop them an email at printcitystudentjobs@mmu.ac.uk. And again, they're fantastic staff in there. They really, really know their stuff. And lastly, for internal resources, we've also got the MMU Make More. So Make More is located in the Chatham building, which is the one we have most of our lectures in. And they're located down on the first floor. They have a Moodle page, dedicated Moodle page. Unfortunately, I couldn't get onto it because I'm a member of staff and I couldn't enroll. So hopefully you'll all have better luck than me. But it's where you can go to book in tutorials, you can request materials, because all of these places have shops where you can purchase the materials for fabrication. Saves you having to order stuff a lot of the time. But essentially here they have a lot of the similar stuff to B15. So CNC, laser cut, 3D printing, traditional woodworking, casting, ceramics, etc. So you can do a lot of the messy stuff here, which is really, really good. But again, fantastic people. Now, let's say, for instance, you're really interested in making something, but you can't find the right material or the right process or right level of detail on campus, in which case you might want to go external. So particularly with 3D printing, the company I would use is Shapeways. So Shapeways is a company based in the Netherlands. So something to bear in mind in terms of things like import tax and Brexit and all of that. There is an implication there. But essentially, they have the biggest selection of materials that you can 3D printing. So I've printed in platinum, gold, rose gold, just about every plastic you can think of, different resins, and these are all from different scales as well, different levels of detail. And again, they can do this stuff down to like the micron levels of detail. especially for the precious metals, like what we discussed a second ago. Essentially they 3D print those in like a wax material. They then cast those and melt out the wax, and that gives them a mold to work with to pour in the liquid metals. And then they just smash away the mold after, and you're left with the metal piece. Absolutely fantastic process. The next one I would also check out is hubs. So it's formerly 3D hubs. It's now just called hubs. But these guys are essentially a collection of makers across the UK. I believe they're now in other countries as well. So for instance, if you had your own 3D printer, you could join their community and print things for people and earn some money. At least make back the cost of your printer, which is quite useful to do. But they now also offer CNC machining. They can also make things like PCBs. And they also offer an injection molding service. So for instance, if you're making something, let's say for instance, you wanted to 3D print some business cards and you had loads and loads of money to burn. You could make a mold for your business cards or get it made here. And then they could then injection mold those to bang out multiples of these for super, super low cost. So again, really, really interesting. Or maybe you want to start selling architectural model making components. It's exactly what happened with 4D Model Shop. You have little 3D scans of people or little 3D models. You make up the tooling, the CNC molds, and then you just essentially injection molding these. And these are exactly what you receive from 4D Model Shop. So again, it's useful stuff. In terms of best practice, there are some do's and don'ts. So firstly, always talk to technicians early on. It's always important to find out things like tool sizes, dimensions of machines, dimensions of materials, what limitations you might hit, and they'll be able to give you some ideas of how you can mix these processes together. So always, always, always engage with the technicians early on. Consider the model's purpose and function. So how will it impact your decisions? So again, if you're doing a structural model, maybe you're going to be using one process over another. Maybe CNC isn't going to be close enough because it might not be able to cut internal edges the way you want it to. Maybe you're going to be laser cutting it instead, for instance. So again, something to think of. And again, and I'll keep saying it, but please, please, please combine processes. Don't just send things to 3D print. I'll be very, very upset. Key things that you shouldn't do are that once you've justified the message your model needs to convey, you should identify an appropriate scale to make it to. So in fact, did I save this correctly? I didn't. Annoyingly, I was writing this on another computer. I haven't copied that across. So key things you shouldn't do is kind of what we were just saying. Don't 3D print it all in one go. Make sure everything's scaled. So don't just send a file as it is. Don't forget to remove your duplicate lines and stuff like that. Essentially just follow the best practice guides and you'll be fine. Considerations, scale versus machine size. So if you know the level of detail you want to represent it, double check that the machine you're looking to use will allow you to make it at that scale and at that size. Most common one is when you're doing site models. So people want to CNC machine terrains, for instance, and then they'll find that actually it fits perfectly on there, but then maybe the 3D printer doesn't do the building. Maybe the 3D printer itself has a too small build plate to 3D print the building to sit on top of the CNC machine terrain. So again, make sure everything is going to be a suitable scale for the objects, but also for communication as well. So in terms of things like level of detail, I know we spoke about that already, just chucking it back out there again. But one thing we haven't talked about much is tolerance. So even if you draw something absolutely like micron perfect in the software, it doesn't always mean it's going to fabricate that way. So a good example of this is the laser cutter. Even though the laser cutter uses a super thin beam of light, it's still subtracting from that material. So it's going to be actually cutting perfectly along your vector line, which means there's going to be an ever so slight fraction that is cutting inside your line, inside your model. So you're going to lose some level of detail, which means things might not fit perfectly together. And that's even more exaggerated for things like CNC machining, to an extent at least, especially if you haven't defined an inner line, an outer line, or cutting on the line. If you meant to cut outside, and if you tell it to accidentally cut inside, obviously your tolerance is going to be off by like 10 millimeters. Nothing's going to fit together. So again, always be careful with your tolerance. And if you're not sure even now what tolerance is, talk to technicians. They'll be able to double check and guide you through it. Now we're right at the end of this guide. So one thing I did want to mention is just again about those tips and tricks. There are various ways to automate a lot of this stuff out there. Most common one that I see students using is this one. So it's just a 3D Grasshopper script, Rhino Grasshopper script, to automate your 3D files. So for instance, we've got some components here that have been extruded and twisted up. We've got other components that intersect it because they're going to act as struts that help add a bit of structural integrity to it. And by setting up this Grasshopper script, and there's a video to this so you can do it step by step. By setting up this Grasshopper script, you can set up a sheet size to lay stuff out on. You can set locations for each of these layers to be set out on as well. You can set up annotations onto it. And you can run all of the commands for things like removing duplicates, making sure everything's a closed boundary, making sure everything's going on to correct layers. All of this stuff can just be automated. So again, highly recommend you start engaging with those. Right, with that presentation, I'm just going to have a quick look in the chat just to see if there's any questions, which there are, which is good. So how do you know if there's double layered lines? Essentially, it's difficult to tell if there's double layered lines. Usually what would happen is you would definitely know once you've made the model if there's double layered lines, because if you're laser cutting, it would make it darker and it would etch it. But the key thing that I would recommend you do is explode your drawings. So you get them back to all individual lines or components, and then use those commands I was saying about earlier. So in AutoCAD, you would be using the overkill command, and that will help you to remove duplicate lines. If you're in Rhino, then you could again use cell dupe or cell dup, which is short for select duplicates. You could also use make 2D in Rhino. Make 2D is a fantastic command. It's my absolute favorite Rhino command, because what that does is it will see everything at face value. So you'll see like what's in front of you, and it will redraw that to its closest interpretation. And it does it extremely accurately. So even if you did have lines there overlap each other, but maybe aren't duplicates, this will still join those together and give you super clean geometry. So again, it's a good way to work. I would always use Rhino for fabrication. It's just the best thing out there. I know there are other dedicated tools. Oh, one thing to mention that I forgot to add to my slide. That Shapeways website is super, super useful in many ways. One reason of which is that when you go to upload components, if I just log in, when you go to upload components to Shapeways, even if you're not planning to print with them, when you upload components, it comes up with like a file checker. So for instance, here's some pieces that I recently had printed in copper. I designed like prosthetics on the side. So I've got my 3D model there that I designed in Rhino. I've got all the different materials and processes that I can print this in. Obviously, these materials can get expensive. So for instance, if I were to print this in solid platinum, it's going to cost me just under £6,000 for this component, which is insane. Whereas if I were to print it in plastic, it's going to be £10. So a bit of a difference. But again, something to consider. But the reason this one's going to cost so much is just because it's a ridiculously complex piece. And there's quite a lot of material density and it's quite a big object. So again, that's why there's that. But yeah, when you upload your files, it lets you go to these tools. So I can open this in the 3D tools. And this will actually give you so many different ways to check your 3D files for CNC and 3D print to make sure everything's going to work correctly. It's the best online checker that I've found. And the best thing, of course, is that it is free. So for instance, I can see my object there. I can see it's passed the mesh integrity and repair because it's repaired something for me. It's got a bounding box. Not sure why it needs a bounding box. That's a massive bounding box. It's telling me that the wall thickness in some places might be quite thin. So for instance, on the material I'm going to print it in, which is this versatile plastic, this can print to a minimum thickness of 0.7 for structural walls. And then any details can be kind of smaller from there. It's just telling me that some elements, like these little red bits over here, some of those are thinner than that 0.7. So I could then go back to software and thicken those up if I wanted to. But everything looks nice and clean. There's no problems there. Yeah, it looks great to me. You can also re-export these as well. So once it's passed those checks, you just go back to your model, and then you can right-click on your model and just download. So again, it's a really, really nice one to work with. If you can't download it from there, you can do it from the previous page. If I just go back a step, it's a notoriously slow website, by the way. No matter where I access it, it's always quite slow. Probably because it's so popular. Being annoying. Right, what was the next question? Do they have any DLP printers available for use? Yes, they do. So the DLP printers you will find in Print City. If we go to their website, I believe there's a bit that says equipment, facilities and equipment. So stereolithography and digital light projection, or DLP. And again, you can see the level of details in these machines. They're absolutely fantastic. It tells you the dimensions of both the SLA and DLP machines. It tells you exactly what the model is as well, just in case you want to find out what materials are available. It tells you the level of detail per micron or per layer. It's fantastic stuff. It really is a good resource. Again, they've got other types of printers there as well. For instance, metal 3D printers they can do. So this one doesn't use a lost wax process where you print in wax and cast it. This one does literally just print directly in metals. So it'll kind of weld these components together. It'll use like a sintering process, just like the SLS one that we mentioned a minute ago. So again, I'm not going to talk about these for too much longer, but have a look through these websites. Hopefully you find them useful. They should be pretty good. Now, what I'm going to do, I was going to quickly load up a file. Oh no, don't want to open all of those. Just going to quickly open a file that I worked on with another class recently. Just want to talk to you about some of the principles and things that you can do with the 3D side of things. I'm just going to wait for this to load. There we go. So let's say I've got this terrain model. This is one that I did with a workshop a little while back, and it's just using Digimap data to generate a terrain. It's got some block buildings that I know are going to have some problems, and maybe I want to do something with this. So for starters, let me put this into shaded mode so we can see the geometry. And I know that when I downloaded this, oh, wrong button. When I downloaded this, it didn't have this base to it. So I'm just going to delete this base away. There we go, something like that. In fact, let's hide this plane for now as well. Yeah, so let's say you've got a nice clean surface. Something like this, I think most of you could probably achieve relatively quick. So a nice 3D terrain. Easiest way to modify terrains, by the way, or to quickly fix things. If you've got a plane, something like this, you can just select it and type in points on, and you can move these points around. So I'm moving those up on the Z-axis. If I wanted to start moving in the middle bits, I could type in the command rebuild. This is one I use quite a lot. I can adjust the number of U and V points, so the number of divisions in each direction. Maybe I want this to be 5 by 5. Type in points on again, and you see I've now got more control points to play with. So for instance, I could start pulling these bits up, I could start sculpting. It's a very, very fast way to make a terrain. Well, I could do the same thing with this one. If I'm using with actual data, for instance, if I've generated a clean surface across it, I could project some curves. Maybe I want to work on this specific element here. I could use the split tool to split the surface from the rest, rebuild it, pull the points around. That means I can then start sculpting it and landscaping it. So again, pretty cool stuff. But at the minute, let's say I wanted to CNC machine this model. Some CNC machines will let you just export surfaces, typically as either STL, OBJ, or 3ds format, but some of them will want them to be closed watertight objects. And I would always recommend you make it as a watertight object. For those of you that don't know what I mean when I say watertight object, I mean something that's solid. So for instance, I could have this box here. I'll copy this over to the side. Just going to explode it. So 2 identical objects. It was a direct copy and paste, nothing else different between them. The one on the left says it's closed, which means that all of these edges are essentially welded together. If this contained a body of water, that water wouldn't leak out, thus it's watertight. Whereas if I select this one over here, I can see this is made up of 6 open surfaces. So because I can select these individually, this isn't going to 3D print. Reason being is that the 3D printer can detect that this one has internal boundaries. It knows that it needs to be a solid object, whereas this one over here, it can't detect an internal boundary. It's seeing each face as a separate entity. So because it doesn't have an internal volume, there's essentially nothing to print. So that's what I mean in terms of watertight. So there are ways around it. Easiest way is just to join. So for instance, if I've got all the faces there, I can select them, type the command join, hit enter, and now when I select it, you see it's a closed solid poly surface. Keyword there being closed, meaning watertight. So I could now 3D print those blocks. And we want to do the same thing with this. Now this is a notoriously complex object, and this is where everyone gets stuck. So the key thing is working out what type of geometry you're working with. Now luckily in this instance I'm working with a surface. Surfaces are by far the easier ones to work with rather than meshes, even though we do want to convert to mesh at the end. But because we're working with a surface, and because we want to turn it into a solid, I'm going to use my solid drop down. Because we're using a surface, I'm going to choose extrude surface. I'm going to choose to extrude it straight. Now for my one, it's trying to extrude it in a weird axis for some reason. So in my command line, I'm going to click on direction. I'm just going to specify top to bottom. So that's my direction I'm extruding in. As you can see, I can now extrude that straight down. If I expand this, you see what it's done. So it looks pretty decent, but because I've extruded it, the profile that I have on the top is now also the profile that I have on the bottom. This again could be really useful if I was making a mold. I could chop these in half, mill the bottom one, mill the top one. I've essentially got something that I can mold between. That's not what I want to do though. I just want to give this a flat base. So again, because this is now a solid object, I can now continue to use the solid tools to add and subtract into this. So I'm just going to make a box over this at the moment. I'm going to move this one into place. And what I'm doing, I'm just moving it until I'm happy with the amount that's sticking out. So now I've got my object to subtract from, my object to subtract. So I'm going to go to solid and difference, and I'm going to select them in that order. So command line tells me what to do. Select the object to subtract from, hit enter. Select the object to subtract, hit enter. And that now chops that bottom away, and it gives us a nice clean watertight object. Notice as well on my one, when I did that extrude, in my command line, I had it set to preserve the surface. So it didn't actually delete anything when I extruded. It still kept it there. But I'm actually just going to hide it for now because I don't need to use it. But now I've got my nice, clean, closed, solid poly surface. So if I wanted to export this now for fabrication, I could go to File and Export Selected. Let me just give this a name. I'm going to call it Fab. I'm going to call this one Base NURBS. It's using NURBS geometry rather than mesh. If I export this as an STL file, I've given it a name, click on Save. Tolerance of 0.01, I would say that's pretty good. It's about as accurate as we're going to get with our machines, so that's pretty accurate for us. And lastly, it's going to come up with one more box asking, well, it should ask at least, if we want to save it as binary or ASCII. We'd want to do this as binary. So I'm going to be patient with this one. It's doing something. There we go. So I'm going to save that as binary. You see, if I saved it as ASCII, it'd be nearly a gigabyte in size. And again, I'm going to show you a magic trick with this in a second. There you go. So that's exported that model. Looks absolutely fine to me. Exported that. I think that was nearly 200 meg. Yeah. So 153,000 kilobytes, or 153 megabyte that ended up being. Now, that could pose a problem for a CNC machine, for instance. It's a lot of data for it to process, plus, takes up a lot of space on your hard drive. So one more thing you could do to this would be to select your object, click on the mesh drop down, and choose from NURBS object. And what this does, it gives you better control over the number of polygons. So for instance, if we're printing this relatively small, if we're cutting it relatively small, and if we're especially limited by the diameter of a mill bit, we're going to be losing a lot of these tiny details anyway. So reducing the poly count probably isn't a bad thing. I'm going to do a couple of these. I'm going to do a high poly count one and a low poly count one to show you the difference. So firstly, even setting that to high poly count, that has processed it super fast. In fact, I don't want to do that one. I want to select the mesh and move the mesh out. Yes. So that's firstly massively simplified it. I'm not quite sure why it simplified it that much. That seems a bit overkill to me. But let's simplify that down. If I'm not happy with that result, I could go again, adjust the polygon count, click OK. I'll get another output. At least I should do if it lets me select it. Mesh, there we go. Drag that one out. So this one's now looking much closer than the other one. I don't know why this one capped out and looked really nasty. It should have looked the most intense. If we were to compare the geometry between these two, they're pretty much accurate. They're pretty much identical. But because we converted this one first, I can still see it's a closed mesh. It's still watertight. But because we converted it first, now when I export it, if I call this one base mesh and click on save, click OK. Both files contain the exact same type of geometry, but look at this difference in file size. So the original one exported at 153 megabytes, the other one exported at 0.5 megabyte. Both of them are absolutely fine for 3D print or CNC, and both will have the exact same level of detail. So again, it's a fantastic way to prep your files and to reduce those down. The only other way you could do it, of course, would be, let's say, if you were to get it down even further, maybe it's not particularly optimized, like all of this stuff I know is pretty much completely flat. All of these panels are flat. Underneath, they're all flat. It doesn't need that number of polygons. I could select this and type in the command reduce mesh. This tells me the number of polygons. So this object has 12,000 polygons. I could reduce it by 50% and see what it does. Click OK. So that's processing up here. I'd say that's probably still accurate enough for what I need it for, especially for CNC. So again, I would select the object, export selected, base mesh 2, I'm going to call this one. And now we've got comparable files, where we've gone all the way from 153 megabyte all the way down to 292 kilobyte. So again, absolutely fantastic stuff. I think there's a question in the chat. No, there's not a question in the chat. Again, if you do have any questions, feel free to start typing them in. I'm going to move on to the mesh side of things now, and this is the final thing I'm going to be showing you today. I'll let you all disappear after this. But essentially, when you're working with meshes, firstly, you might get duplicate objects, which is the case in this case. So as I hover over both of these options, I can see there's two things in the same place. If I were to go to Edit, Select Objects, Duplicate Objects, you see it will highlight anything that's a duplicate. And now I can just hit Delete, and now it's cleaned those out. So that's that cell dupe or cell dup command I was telling you about earlier. Super, super useful. Saves you having multiple objects in the same place. But let's say I wanted to 3D print these buildings to sit on top of this. In fact, there's two things I'm going to show you. This is one. I'm going to show you how to extract contours for laser cut models. But let's say I want to 3D print these buildings. Currently, it says it's a closed mesh, which is really good. This one says it's a closed mesh. Annoyingly, they're all perfect, which is typical. But let's say I had a mesh that sits on the edge, another way to trim this down. You know, I don't want to 3D print it over the edge. Then what I'd probably want to do is just make something to cut it against. So I'm just going to make a little line across there to use as like a cutting line. So this bit just there. And what usually happens is people get a bit stuck because they'll try typing in the command trim. It's not going to work because I can select the cutting object, I can hit enter, but when I try and select mesh, I can't select it. The reason being is because it's mesh geometry, you need to use the mesh tools. So if I go to mesh, edit tools, mesh trim, I can now trim this away. So cutting object, same as before, hit enter, thing to trim away is this mesh, and now it's trimmed it down. The problem you'll now have, if I just zoom into this, the problem you'll now have is it looks fine all the way around here, but when you get around the back, you see it's now made it become an open object. So I wanted to show this because it's a really common issue. Even if you've tried modeling things correctly, sometimes you still get open objects. And sometimes if they're not planar, you can't cap them as a solid. So it's better just to convert these to become a mesh object, like we did with the terrain, and then repair them as meshes. And there's various things we can do with this. So for instance, I could select the object, go to mesh and mesh repair, fill all holes. And that's now made that a closed mesh. That in theory would 3D print. There's a slight problem with it, and I can see it by looking at it. All of these faces look correct, but when I look at the back, it's doing something weird. It's gone shiny. And this is a common issue called flipped normals. And for those of you that have ever tried 3D printing from SketchUp, you will probably be aware of what this is. It's where faces are facing the wrong way, and it means it's not a closed object because that face faces the wrong way. If you make sure the faces are facing the correct way, for instance, if I had a cube, if all faces were facing inwards towards the center, then it means I have a unified model. So that's what I need to do with this. I just need to unify it. And my technique for that would be to fill all holes, and then straight after I would tell it to go to repair tools, rebuild mesh normals, and lastly I would choose unify normals. So it actually fixed it on the first try, but doing those three in that order 9 times out of 10 will fix your mesh files. Anything else that's remaining, for instance, if I undo this again, if I go back to where there were problems, anything else where there's problems, you can select the mesh. You could also type in the command mesh repair and click on check mesh, and this will tell you everything that's wrong with it. So for instance, try not to click everything. So that one I just selected, it tells me it has naked edges. So it means that it's got open faces, it needs to be closed. Naked edges can cause problems if the ultimate goal is STL output, which it is because we want to fabricate it. So I could then, well, I need to check mesh again. I could then click on next. I could either choose repair, or if it came up with something more serious, I could choose it to remove duplicate faces, remove non-manifold edges, all the common problems you usually get with 3D print files. This is how you do them. The one where it just says it's got open edges, but that's an easy one. We did that before. It is just a case of filling those holes. So again, nice and easy. Now the absolute final bit I'm going to show you before I let you all go is just how you can start combining some of these things. So for instance, we looked at those terrain models. Let's get rid of that. We looked at some terrain models, namely the topographic ones. If I just hide all these for a second. So let's say I wanted to make a terrain model of this. Very, very easy to do. Maybe the CNC machine's out of order this week. Maybe we've destroyed it. Maybe it's been sold off. It hasn't. It's working fine. But maybe I need to use a different process. Or maybe the scale I want to do it to is just not suitable for CNC or something. You know, I could still easily fabricate this on a laser. Very, very easily. So the way I would go about doing that, I would scale it down to the scale I want my model to be. So if I quickly measure this, I can see that this has a height of 96 millimeters. If I wanted to convert this, firstly I would make sure I would scale it down to the scale. This looks like it's about right. So it's going to be about 10 centimeters tall, 541 millimeters wide by 798 millimeters long. That would technically just about fit in the laser, I think. No, it's not. It's not going to fit in. So because it's not going to fit in, I'm actually going to do this half the scale. So let's do this 0.5. Missed a couple of buildings there, but we'll forget those for now. Just turn those off. So now I've got it to a correct scale. Always good to double check before you start chopping this up. Now I'm happy with it. I can now start extracting contours. So I'll select my model, type in the command contour. I'm going to tell this to go from bottom to top, and I recommend that you do select a low part of the model. And then in my command line, I can now type a distance between the contours. So this would be the thickness of your material. So let's say I'm doing 2mm thick plywood, for instance. I'll type in 2, hit enter. That's now going to extract all of my contours from the 3D model. And because it extracts these as vectors, it means that I can put these out onto layers. So for instance, everything on this layer, that could all be cut on one sheet. That could be done, set to be RGB red and cut out. I would then do the one on the next layer. So it starts getting annoying trying to select everything, but you get the idea of what we're trying to achieve. And if you wanted to see what a model like that would look like, fabricated, it's just a case of selecting these, going to solid, extrude curve, straight. And we already know the distance between the contours was 2, so my extrusion distance is going to be 2. Hit enter, and now I've got this nice contour model. So you even get to preview it before you fabricate it. It saves you so much time working out that things aren't quite the way you want it to be. And again, if I weren't happy with the level of detail with that, well, that's super easy to resolve. I'll just make another one. So let's say, for instance, I'll select my object again. I contour it. Select it from bottom to top. Maybe I want to do it every 1mm. Maybe I want to add more resolution in. So I'll type in 1, hit enter. You see it's a significant number of contours this time. I'm going to go to solid, extrude. This time it's doing it in the wrong direction. So again, in my command line, I'm going to type direction, just do top to bottom. Again, I'm just going to extrude those by 1, because my contours were 1 this time. In fact, it doesn't look a huge amount difference. We can see along here, we've got a lot more detail compared to here. So again, it gives you that good opportunity to kind of explore and play around with your models. Now, I think we've got 15 minutes left, because it's supposed to be a 2-hour workshop, and I'm quite knackered. I'm going to take any final questions if anyone has them. If not, then we can wrap up there. So you can either unmute your microphone, or you can type in the chat if you have any, or you can just say, bye Jay, thanks, and then you can leave. It's up to you. Any questions from anyone? I don't think there's any questions, unless anyone's typing things out in the chat. What I'm going to do, I'm just going to very quickly check something on another machine. Another machine in this room's just flared up. I'm going to come back in about 30 seconds to see if anyone's typed anything. If not, then you're all free to leave. And next week, we've got an intro to SketchUp and Saphira. So if you're interested in learning how to use SketchUp and do some environmental modeling, highly recommend that you come along to that. It's going to be a really useful workshop. I think that one's a 3-hour workshop as well, run by Mahmood. So yeah, oh, I can see someone is typing. Okay, I'm going to be back in 2 secs. I'm just going to check, see what's happening with this other machine, and I'll come back and answer the questions. There we go, I'm back again. Right, so I see. There we go. So you mentioned it wouldn't be a good idea to just make a final model at the end of our project, saying it might look lazy. Can you explain what you meant by that? So it's not just a case of not just making a final model at the end. That's absolutely fine to do. But let's say you made a 3D model of your building. Maybe you did it so that you could extract technical drawings. Maybe you made the model so that you could do some visuals or animations. But what you wouldn't want to do is just select that entire model and just print the whole thing off in one go in a piece of plastic. So for instance, that model I just had open, in fact, if I undo this many times, I'll get back to the original. You know, something like this. That's as far back as I can go, that's a shame. This one like this, if I were to extrude the base of this, I think CNC machining that would make sense because I can get all of the level of detail of all of this being carved out. But then maybe I want to laser cut a piece of acrylic to represent the water, for instance. So I could simply make a plane that goes around this. I could trim that plane against this terrain surface so it cuts along the outlines. And then I could explode that to get the curve so that I could laser cut all of the sea. And then maybe I'd make some little sticks to hold up the acrylic, and then I'd have a really, really nice clean model. Whereas if I were to just take this whole thing with the buildings on top and 3D print it, then essentially it would look a bit rubbish. It would just look something like this. If I just override these materials. Yeah, so it would just look something like that without all of these nice curves. If someone just printed this out as like a blob, I'd be quite disappointed personally. I don't think this communicates anything. Like, I can see there's buildings on the top, but I can't see which one's the focal point. So I would maybe do this as like a context model if I was going that small, but I would then at least do something special with the building I'm focusing on. So again, it needs to be like a justification of what you're doing with it, I would say. Does that make sense? Hopefully it makes sense. There's more to the question. What if it was a laser cut model, for example, and not a 3D model, just as a presentation model to show the facade of our buildings? Yeah, that's fine. I mean, if the whole thing is laser cut, then that's fine. You know, you're using one process, but then you might want to start mixing it up with different materials. So you could have laser cut wood, for instance, to represent all of the structural elements. Maybe you're going to have some laser cut card to do like some facade details or something, because you could obviously print onto card and then laser cut it. So you can even have like detail into it. And then maybe you're going to laser cut something like PETG or some acrylic to act as windows. So having that contrasting materials is what would make that acceptable. If it's not a presentation model, if it's a working model, then that's absolutely fine. Because, you know, it's just there for kind of form finding and testing, in which case it doesn't need to be that strict on your processes. But for presentation, yeah, always combine some processes. Cool. Right, I'm not seeing any more questions coming in through the chat, so I think we're going to leave it there, finish about 10 minutes early today. But yeah, come to the workshop next week and I'll see you then. Bye.